Recall that this is the gamma function, and so this is gamma k. If we do gamma k plus 1, then in the place of k here we have k plus 1 and then minus 1, which is just k. And so the integral from 0 to infinity with the integrand t to the k times e to the minus t, this is k plus 1. And then also recall the formula gamma k plus 1 is equal to k times gamma of k. And so if we have a random variable x, and it has we say that the random variable x has a gamma distribution if it has this probability density function. So if a random variable x has this function right here as the probability density function, then we say that the random variable x has a gamma distribution. And here k is positive, theta is positive, and then x is also positive. And now we want to find the expected value of the random variable x, the expected value or the mean of x. And the expected value of x is defined as the integral from 0 to infinity with the integrand x times f of x. And we want to show that the mean of x, or the expected value of x, is equal to k times theta. So this is what we want to show. So here we have x times f of x, which is x times the probability density function here. This integral is with respect to x. Therefore, this expression 1 over theta to the k times gamma k, this expression is just a multiplication constant. So we can move it and place it in front of the integral. This is x to the first times x to the k minus 1. And so it'd be, we just add the exponents, it'd be 1 plus k minus 1, which is k. And now we want to find this integral right here, the integral x to the k times e to the minus x dividing by theta. So let t be x over theta, which is the same as 1 over theta times x. dt d theta will be 1 over theta. So dt will be 1 over theta times dx. And so we have theta times dt is equal to dx. From this equation, multiply both sides by theta, we get x is equal to theta times t. We need x to the k, so raise both sides to the power of k. So we have x to the k times theta t to the k, which is theta to the k times t to the k. And so for this integral, in the place of x to the k, x to the k here, we have theta k t to the k. So in the place of x to the k, we have theta to the k times t to the k. X over theta is t, so we have minus t. dx is theta dt, so we have theta dt. Theta to the k times theta is theta to the k plus 1. And then we can move it and place it in the front. As mentioned earlier, t to the k, the integral from 0 to infinity with the integrand t to the k times e to the negative t is gamma of k plus 1. Gamma of k is t to the k minus 1 times e to the negative t. Gamma of k plus 1 is t to the k plus 1 minus 1, which is t to the k e times e to the minus t. And then gamma of k plus 1 is k times gamma of k. So this integral right here is gamma of k plus 1 theta to the k plus 1 dividing by theta to the k is just theta. Gamma of k plus 1 is k times gamma of k. And so what's left? And then we have gamma of k divided by gamma of k, which is 1. And so what's left is just theta times k. And so if the random variable x, if it has a gamma distribution, then the expected value of x, or the mean of x, is k times theta.